Hi everyone, thank you for tuning in. My name is Nienke van der Marel and I'm a Benting Fellow at University of Victoria. And today I will tell you about a direct link between disk structure, disk evolution and exoplanet demographics, based on a recently submitted paper by myself and Gijs Mulders. Over the last 5 years, ALMA has provided us with many large disk surveys, snapshot surveys of 1 to 2 minutes per source, mapping hundreds of disks in nearby star-forming regions, with ages of about 1 to 10 million years old. These surveys provided us with dust and CO fluxes with which we can compute gas, disk, and dust masses. So together with the ages, we now have statistics of disk mass and evolution. One of the results of these disk evolution studies is the following plot, a cumulative mass distribution diagram of the dust masses in different regions. What we can see in this plot is that the disk dust mass strongly decreases with age, with the highest dust masses in the youngest regions. In this plot, we see the correlation between the dust mass and the stellar masses. The highest mass stars have the highest mass disks, but also we see that this correlation steepens over time, which tells us that the decrease in dust mass is the strongest for the low mass stars. So I decided to merge all of these large disk surveys together into one very large disk survey of more than 700 targets in nearby star-forming regions. I grouped these targets into 3 different age regimes: young, intermediate, and old. And I classified each disk as either a transition disk with a large inner cavity, a ring disk with narrow gaps, and all other disks without clearly resolved structure as either extended or compact with a threshold of 40 AU. What we can see in these plots, in these histograms, is that the so-called structured disks, so these are the transition, ring, and extended disks, have a high dust mass compared to most of the disks, and they retain that high dust mass over time. On the other hand, the majority of the disks, the compact disks, have a somewhat lower dust mass, and this dust mass actually decreases over time. So this suggests that there are 2 separate evolutionary pathways in terms of dust evolution, either structured disks, likely containing pressure bumps, preventing radial drift, and compact disks, which can be explained by mostly radial drift dominated evolution. So if we assume that all these disks with gaps are caused by pressure bumps, and we think that these pressure bumps are caused by planets, that means we can say something about the kind of planets responsible for these gaps. And several people have studied this question: what is the minimum mass required to clear a gap in a disk? And although these studies all show that there are some dependencies on different disk and stellar conditions, overall, the conclusion is that a detectable dust gap requires a minimum planet mass of about 10 to 20 Earth masses. So with this information, we can now link disk morphology to different planet mass ranges. Transition disks with deep wide cavities are thought to be cleared by super Jovian planets, so more than 1,000 Earth masses. Ring disks with narrow gaps require at least 20 Earth masses and up to about super Jovian level, 1,000 Earth masses. And finally, the compact disks, which don't have any gaps, may contain planets, but those planets cannot be more than 20 Earth masses. So how can we test this? We want to compare our disk morphology and our disk demographics with exoplanet demographics. This is a plot of the observed exoplanet distribution of the planet mass as a function of semi-major axis. But to do the comparison, there are 2 problems. First of all, the typical gap radii are located at tens or even hundreds of AU, and exoplanets as these wide orbits are rare, even after correction for detection biases. So the way to resolve that, at least for the purpose of this study, is that we assume that planets migrate inwards and end up at a small semi-major axis in the final exoplanet population. So now that we are ignoring these orbital radii, we're going to take a look at the stellar mass dependence of our disk demographics, our disk morphologies. So I've grouped all my disks into 4 different stellar mass bins, up to 0.5, 0.5 to 1, 1 to 1.5, and more than 1.5 solar masses. And in each pie chart, I show the fraction of the different types of disks that we find there: transition, ring, extended, and compact. These pie charts show that transition, ring, and extended disks are much more common around the highest mass stars. Essentially, there is a strong stellar mass dependence for the fraction of structured disks. So we would like to compare this now with the exoplanets, but we need to resolve a second problem, which is exoplanet detection biases, planets that cannot be detected with current surveys. So essentially what we need are planet occurrence rates. And several people have computed these kind of occurrence rates based on the available observations. One of the results is that the giant planet fraction increases with stellar mass, and that the planet fraction of sub-Neptunes decreases with stellar mass. So the combination of all these occurrence rates can be merged into an exoplanet population simulator, for example, EPOS, which was developed by Gijs Mulders. So I asked Gijs Mulders to compute different planet populations for the stellar mass bins in my disk sample. And this is the result. In the top row, we see the stellar mass dependence of the morphologies of the disks, just as I was showing before. At the bottom, we see similar pie charts, same stellar mass bins, but now for the occurrence of giant exoplanets in different planet mass ranges. As we can see, there is almost a perfect match between the two pie charts, where the highest mass planets correspond to the transition disks, intermediate mass planets correspond to ring and extended, and there's and then even lower mass planets correspond to the even lower fraction. So this tells us that disk gaps are very likely linked to giant planets with a strong stellar mass dependence. A second comparison was done with the close-in super-Earths, also called Kepler planets. In this case, we have to do a correction for binaries, but with that correction, we actually find that Kepler planets' fractions and the stellar mass dependence corresponds almost perfectly to the fraction of compact disks. So also there, we can basically say compact disks must be linked to Kepler planets. Kepler planets must form in these kind of systems. So the combination of these results led us to create this new evolutionary scenario. On the top, we describe the different correlations between disk mass, stellar mass, and planet mass. And then, assuming that there is a certain threshold in the disk mass, we propose an evolutionary scenario where above the threshold, disks are able to form giant planets. These giant planets lead to pressure bumps in the disk and a so-called structured disk, which we can see in the observed disk morphologies. On the other hand, if no giant planets are formed, the dust in the disk must drift inwards, essentially forming a compact dust disk. In a compact dust disk, the dust pebble flux is high, and that enhances the formation process of super-Earths rather than terrestrial planets. And this again corresponds to the exoplanet demographics. This scenario has a number of implications. First of all, it suggests that giant planets must form early, in less than 1 million years, in order for us to see the structures in protoplanetary disks, while super-Earths must form later on. It also suggests that there are no giant planets and super-Earths in the same system. This is true for the solar system, but in exoplanet demographics, this is still highly debated. Third of all, our scenario requires inward migration. Planets may form, or at least be located, at large orbital radii in the disk phase, but later on must migrate inwards. And this would be reflected in the exoplanet atmosphere composition. So this is a very important thing that we can test with JWST. Another comparison that I did was between protoplanetary disks and the morphologies there in comparison with the occurrence of debris disks. In this case, I chose the occurrences of cold debris disks as traced by the Herschel Debris Survey. Also for debris disks, there is a very strong dependence with stellar mass, suggesting that the progenitors of the debris disks are in fact the transition and ring disks. And for further discussion about this topic, I refer to the talk by Arnaud Michel. So to summarize, this study shows that there are two evolutionary pathways for structured and non-structured disks determined by the presence of pressure bumps. The occurrence of structured disks matches with that of giant exoplanets, assuming inward migration, and the occurrence of compact disks matches with close-in super-Earths. These results suggest a complete picture of planet populations, planet formation, and protoplanetary disks. Thank you for listening, and if you have any questions, don't hesitate to send me an email. Thank you.